Brian Kurz. I have Michael Hans here on my left and Jack Grimm. Hello, I'm Brian Kurz. I have Michael Hans here on my left and Jack Grimm on my right, and we are doing work and energy. Man, what a great subject. We're really going to expand on this in the next 10 minutes. So first, work is given in the force parallel to the distance of the object's motion. So for example, if you have an angle above the horizontal, you need to give it in work times force times distance cosine theta in order to get the force parallel actually with the distance of the object's movement motion. Alright, now for the units, because force is in newtons and distance is in meters, you multiply those, work is given in newton meters, which also equals a joule. Alright, now how work and energy go with each other. Work equals change in energy. So there's three types of energy, and we're going to give the first one, kinetic energy, equals 1/2 mv squared when m is the mass of the object and v is the velocity. The potential energy for the gravitational potential energy is mgh when m is the mass. G is the acceleration due to gravity, so 9.8 meters per second squared. And height is the distance from the ground level to where the object is. And the last one is when you have a spring, the elastic potential energy, and that is 1/2 kx squared. Where k is the spring constant, and x is the displacement from equilibrium for the spring. Alright, now calc relationships. So now we're going to use calc to find the relationships between power, energy, and work. So first, because we haven't talked about power yet, power is the derivative of work. So it's the change of work over the change in time. So first, if you're given the work, you can find the derivative of that to get the power equation. And next, so say now you have a potential energy, gravitational potential energy versus time graph. You can find the opposite of the slope. So the opposite of the slope of that is the force. So pretty much you can find the derivative of a potential energy gravitational equation versus time, and you have to take the opposite of that in order to find force. Lastly, we have work is the antiderivative integral of a force over displacement equation, because think about it, work equals a newton meter, so then if you find the integral, the area under the curve, the force is newtons and distance is meters, so then you have newton meters. Alright, lastly, we're going to do Hooke's law. Hooke, man, what a guy. Man, what a guy he was. Alright, Hooke's law is it's the reacting force. It's like the force going the opposite direction equals negative kx, where k is still the strain constant, x is the distance from equilibrium. So, and it's only negative because it's going the opposite way of the motion. It's the reacting force.
Alright, so our first problem, we got a 15 kilogram crate initially at rest, slides down a ramp 2 meters long and inclined at an angle of 20 degrees with horizontal. There is no friction between the ramp surface and the crate. What is the kinetic energy? What is the kinetic energy of the crate at the bottom of the ramp? Alright, so we got a ramp right here that's 2 meters long at the top and an angle of 20 degrees. We're going to just use an energy, a little easier than kinematics. It can still be done with the kinematics, but energy is the way to go here. So, set up a little equation where you got potential energy initial plus kinetic energy initial equals the potential energy at the bottom, which we'll call the final, plus kinetic energy at the bottom. So the question is asking, what's kinetic energy at the bottom? So we want to solve for this. So potential energy initial is mgh, where h is the height right here, plus kinetic energy initial, which turns out to be 0 because it is not moving at the time. So there's no velocity. So it would be 1/2 mv squared, but v is 0. And that equals potential energy at the bottom, which is mgh final, which will turn out to be 0 too, plus kinetic energy final. So to solve for the height, use a little bit of trig. So sine of 20 equals the height divided by 2, which is the length. Do a little algebra right here. You got 2 sine of 20 equals height. And for your height, you get height equals 0.684 meters. That'll help us a lot in this equation. So, if you want to plug in some numbers, we got 15 mass times gravity, 9.8, times height, 0.684, plus 0 equals 0 plus kinetic energy final. So you get 100.548, that's going to be in joules because it's energy, equals kinetic energy final. That's a little bit of energy for you right there. What a problem.
Alright, so our second example is a hill is 100 meters long and makes an angle of 12 degrees with a horizontal. As a 50 kilogram jogger runs up the hill, how much work does the gravity do on the jogger? So first we're going to draw a nice little hill. Meters long, 12 degrees, and what we're trying to do right here is find the force of gravity in the x direction. So Fgx is equal to mg sine of 12, and then we're going to plug in some numbers for that. And we get 50 times negative 9.8 sine of 12. So simplifying that, we will get a value of 101.877 newtons. And now, since we got the force, we do work, which is work times the force. Work equals force times distance, so we know the force is equal to negative 101.877. We know the distance is 100 meters. So we put that in, and then we multiply those together, we get a work of negative 10,187.7 joules. Good.
Good job, Jack.
Great work. Thank you, my
Good job, Jack.
Thanks, colleague.
Alright, our third and final problem here. We got part A, estimate the work done by the force measured in newtons, shown on the graph in displacing a particle from x equals 1 to x equals 3. And then part B, I'll talk to you later about part B. So first, for part A, for estimating the work under the curve, so work done would be the, for work done, you get the integral on the force for time graph. So, we're going to use LRAM for this. So, from 1, from here, to x equals 3, right here. So we're going to use LRAM, so you need to get, we're going to use the area of like rectangles for this. So, the area, so 0.3 in between here, 0.2 between here, 0.3 between here. It's a little pattern we got going on. 0.3, 0.2, 0.3, 0.2. So those are going to be the widths of each rectangle. using this, that the left point on the first rectangle right here, it's got a height of about 9, so 0.3 times 9. The next one is 0.2 the width times the height, 5.8. Next one is 0.3 the width times height of 4, 0.2 times height of 3, 0.3 times the height of 2.2, 0.2 times height of 1.8, 0.3 times the height of 1.4, and 0.2 times the height of 1.1. Using our mathematical skills, we'll get that equals to a total of 7.32 Newton meters. That's a pretty good guesstimate we have right there, but we want to use it more exact. We use a little bit of calculus. So, we'll set up an integral right here. Get the integral from 1 to 3. Use our equation that is given by f equals a over x squared, where a is 9, so we'll plug 9 in. So we got 9 over x squared dx. We'll do that in our head real quick. That's going to be 6 Newton meters, and that is the answer that we get up in the question right here. And that is